Hello, everybody. I'm so sorry to be not there on Saturday. Today is Thursday, and I'm here in Pennsylvania. I couldn't make it to our conference. I was extremely excited to join you in person. Excited about some of the presentations, not only at this session, but also at other sessions. But mostly excited about hanging out with you in the social, dinner and get-togethers at the after Saturday, Saturday night. So I was looking forward to being in St. Louis Saturday night, and I would like to thank very much Professor Johnson for inviting me to participate in this conference. It's really great. For the record, the last time I was at a in-person conference, I think it was the year 2012, and the last time I gave an in-person invited seminar at a university, it was 2017, I believe. So you can imagine, it was pretty exciting to move to go to St. Louis and to hang out with you. And I'm very sorry that I cannot be there, but I cannot be there. So thank you so much for having me here. My name is Hector Mera. The title of my talk is Goodhart's Law and Human Computers. It's a collection of short stories on math pedagogy. So I will tell you about human computers and about Goodhart's Law, and I won't have the time to go through Bloom's taxidermy and examples of practice. What I will do instead is to put a bunch of assessments and other recordings into the description. Thank you. So one thing I would say two things about my pedagogical approach. One is that it's a very flexible, built-on experience. That by no means I'm a quote-unquote theoretical pedagogue or a thought leader. That really, I teach for a living, and it's very easy to come up with theories and thoughts, right? But it's extremely complicated to make it work in a classroom in general, right? So the pedagogy I use and I develop on my own, I have deployed from Math 080 to Math 299 in face-to-face classes and online classes, and more than about 1,000 students have been involved in these pedagogical experiences. I would say that I'm aware that I'm preaching to the choir. I'm preaching to the choir, to the nuns, to the priests, to the bishop, to the pope, because you are the community, the mathematical community of educators that understands better than anybody else the importance of bringing authentic mathematical contexts, real world scenarios, and real world practice of math, like on the job practice of math to your educational experiences. So it's really been rewarding for me to participate in the past at the Semiote conference and to be a part of this community. Um, so the only thing I would say about my pedagogy, because of time constraints, is that I make an operative separation between math and computation. This is not a real separation, but just operative, you're right. And an example of math would be something like the fundamental theorem of algebra, the factor theorem, or the complex root theorem. An example of computation would be something like factor this polynomial, right? And in my courses, computation is always like the most important topic is gonna be the concepts, what I call mathematical concepts. And computation always plays a subservient role, secondary role, to concept. It plays the role of service, it's at the service of concept exploration and the illustration of mathematical concepts. It is, computation is the mathematical experiment, in my view. So I will skip everything else about pedagogy and let's start with the stories. So I was told about Wim Klein, which was the human computer, the best human computer at CERN, by Professor Carlos Pajares at the University of Santiago de Compostela. This is my alma mater. He was a great physicist. He is a great physicist, I believe. And he worked at CERN, so he had this aura of like, wow, he had been at CERN and he had all anecdotes. But the most impactful anecdote was when he told us that, something about along the lines like, well, while I was at CERN, we had great computers. And the best computer, his name was Wim Klein, right? He revealed, right, that the best computer at CERN was actually a human. And he told us that they had a computer room at CERN, or computer rooms, if I recall properly. and those were arranged into rows of tables. In the first row, you would put the theoretical physicists. These are kind of applied mathematicians, but that use in physics we express the physical principles as mathematical. They are mathematical in nature. So from those we derive equations, right? So you can imagine the theoretical physicists like computing something like, I don't know, a cross section for neutron capture. They get to some integral, pass it to the back to the human computer, and the computer that everybody went behind was being claimed, that guy that I showed there with those numbers. In the second row, you would have organizers and computers. The organizers and computers would be people who know algorithms and also computer scientists, but human computer scientists. So if there was a very complicated computation to be performed, those organizers will organize their computers, their human computers, in certain patterns. So, you know, the computation information would be transferred between those, right? Like, you know, if they were GPUs or CPUs, right? And at the last row, you would have the calculators, right? And this would be people who execute algorithms. Step one, do this. Step two, do this. Step three, do this, right? And, you know, because this is a pedagogy talk, what I want to do is to overlay Bloom's taxonomy on top of this. And to reveal to you that I believe that our students, what we actually do with our students, is make them work as human computers. And that, in the language of Bloom's taxonomy, means that we are utilizing the lowest rank of that construct, the Bloom's taxonomy, that one, number one there, right? They just execute calculations. So they give them some procedure and they will execute that procedure very well. Very well. But they don't know what they are doing. They don't know if they are calculating a neutron capture cross section or a decay rate for, you know, I don't know, tau muons, right? For some muonic particle or something. It's interesting experiment that you can do is to go to the Internet Archive and look for a very old dictionary. If you do that, you will see that they refer to computer as a human, right? A person, one who computes, a reckoner, a calculator. And in the modern definition, of course, is a machine. So who would you say is better at math? Professor Pajares, this guy here, or being claimed, which is this other guy? Let's see if I can move myself. This guy here, this is being claimed. If you look at the what he has in there, he has in the blackboard all numbers, right? And if you look at the blackboard of Pajares, you cannot see it so well. You will see that that it has like symbols and graphs and sketches, right? It's a complete different type of blackboard, right? So in my opinion, the one that is better at math is Pajares by a mile, right? By a mile. That for me was extremely revealing as an undergraduate student, as a young undergraduate student, as a wannabe physicist. You know, I was mesmerized by not only by the notion that computers would be humans, right? Although I didn't know very much about computers back then, but I imagined that people would do their own computations in pen and paper, or with a calculator, or maybe they would go to a machine, right? But no, they use human computers. I remember thinking, you know, what does it mean to be good at math? All of the stuff that we do at the college, right, seems to be computation, right? We are like human computers. Nowadays, again, you know, what does it mean to be good at math in the context of college education? What skills do we mean by that? What skills do we teach? Actual legit mathematical skills. What are, if can you enumerate the skills, legit mathematical skills that you are using in your math courses? How do you teach them and why do you teach them in that way? And how do you test for them? So this is what this talk is about. So one thing I would like you to consider is the relationship between understanding something and being able to compute something, right? So imagine that you understand something. Can you compute it? Imagine that you can compute something. Does it mean that you understand it? And I dare to say that the answer to these questions is no, and a very trivial no. You know, the human computers at CERN, at the final row that are executing algorithms, they don't really know whether they are computing a differential cross-section or a decay rate. Doesn't really matter to them. They just execute those operations. They have no understanding, although they compute. The same goes to about your TI-84 or mine in this case. Well, it's mine. I found it in a garden. Um, Somebody discarded it with good reason. And the other thing is also not true, right? If you understand something, it does not mean that you can compute it. For example, I can tell you that if you give me a third-degree polynomial and you give me pen and paper, I won't be able to factor it or find the roots, right? For any third-degree polynomial. If you generate any random third-degree polynomial, maybe I could compute it, but it will take me, a day. I don't have it in me, right? I won't. Another example is the many-body Schrödinger equation, non-relativistic, right? So with that equation, we can calculate all the optical properties, all the electronic properties of any material, right? The thing is that we cannot really compute it for numbers of electrons around 10 or 20, maybe even, right? Depending on the symmetry. So certainly you understand things that you cannot compute, and you can compute things that you don't understand. So what do we mean by being good at math at the college? Well, what we mean is solve equations, integrate, differentiate, combine vectors, factor completely, factor polynomials, divide polynomials, all of that, right? It's purely operational, it's purely computational. I distinguish between math and computation. This I call computation. But there are these other skills. Imagine creativity. Creativity, I think, is chief, one most important math skill. How can you be a real mathematician in a way without being creative? Because if you are a real mathematician, human knowledge was here and then you created something. Now human knowledge, maybe it's just a little bit farther, but there was nothing there and now you created it. So you do have to be creative. A creative person is gonna struggle with this, right? It's gonna struggle with this. Step one, do this. Step two, do this. Step three, do this. That is anti-creative. And how are you gonna be passionate if you don't see the value in what you do, right? If you cannot relate it to the real world. Again, this is one of those cases when I'm preaching to the bishop, right? You know what I'm talking about. Of anybody in this country, you are the ones who understand me. So let me show you actual examples of classroom successes and failures where this distinction becomes obvious. So here is a typical problem from my Open Math, and shout out to my Open Math, fantastic work. Thank you so much for what you do. Those contributors, I love you very much. Thank you. These are the problems that we use in our general education Math 106 class. So there is a unit, statistics, and they have to solve 15 of these or something like this. Here, and the problems are all the same. Here is a list of numbers, find the mean, find the median, find the standard deviation, repeat for the next list of numbers, and do that 15 times, you get your homework credit. They don't know what they are doing. Literally, they don't have a clue about what they are doing. Now here is a problem that is for my final exam in the very same course, in which I actually test the knowledge of the students if they really do understand normal distributions, mean and median. So in an imaginary suburb, let me maybe go a little bit closer. You have like 90% of the population. It's a very rich suburb, so they make 1 million, say, and the standard deviation is 100,000. And 90% of the suburb, that's their income. 10% of the suburb, they have income of 10 million and a standard deviation of 1 million. Estimate the mean and the median based on that information. The mean is 9 ones and 1 10, so 19 divided by 10, 1.9, and the median is 1, right? And then I give them a sample of, a sample of a random, yes, a random number generated from that binormal distribution, right? 10 of them. You know what happens? And then I ask them to calculate, to do the standard exercise. So they have to do exactly this, but now with a list of numbers that has been generated from somewhere, and it has a context, right? So the students calculate that, and then I ask them which statistic better represents the population and why. And in fact, the answer would be both, right? Because the difference between the mean and the median tells you a little bit about the distribution, probabilistic distribution of incomes in the population. one thing I love about these problems that are kind of like difficult to contextualize, and this was an open book exam. I have some problems with my lighting here. Yeah, an open book exam. So, some students, what they did is actually solve the experiment first, right? And then go back, and kind of reason afterwards, right? And I love when they do that. Some students, they actually understood it from the top and proceeded downwards. So this was a win because I think about 3/4 of my class managed to solve this problem very well, right? At least well enough to pass it for me to pass them the problem. Um, I know what I did right in that case, but I didn't train my students into solving this specific problem, right? I trained them into understanding the difference between mean and median and how to compute it. That is important for what is coming. The next thing is an example of failure in which the students actually really fail. So this is a standard problem, match the rational function to the graph, right? And the students solve this algorithmically. So what they do is to say, if it crosses the axis at 2, put x minus 2 in the denominator. If it swings like that at 1, put x minus 1 in the denominator. And they knew that this was going to be in the exam. They have a homework in my open math where there are 10 of these. So they are really very well prepared to solve this. 1 out of 20 failed this question. Now, if we change the problem slightly, so rather than showing between 0 and 4, where all the interesting thing happens, we just saw the asymptotic region for large x between 20 and 24. Then what happened? Well, 4 students out of 20 solved this question correctly. So changing just like the range of the plot, the horizontal range of the plot, the number of students who completed with 19 out of 20 to 4 out of 20, something has gone wrong, right? My own failure, but the failure of the students too. So you can see that this problem here, that so many students fail, is a metric for me, right? It's a real metric of students' knowledge. Only those 4 students are quote unquote good at math. The other 16 are not good at math. And what is happening with the other problem, I believe, right, this problem that everybody got right, is that it's a metric for me, but a target for the students, right? The students do not really care about asymptotes. What they want is the credit, so they learn that if I does like this, put x minus 1 in the denominator. They solve the problem algorithmically. Bottom row of the computer room. Now here is what we call the calculus readiness package. And if you look at the problems, let me see. Simplify, expand, factor, simplify, rewrite, solve, 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 solve. Graph, there is one graph. Convert, find the exact values. And then I would say, if you divide between, distinguish between math and computation, it depends where you put, the line, where computation ends and math starts, right? For me, I would say something like, this calculus readiness package developed at my college has math 3, computation 13. Maybe for you it's different. Maybe, I believe the people who develop, for them is computation 16, math 16, computation 0. Maybe you think math 10, computation 10, right? Myself, I see this as essentially math 3, computation 13. The important thing for our educators is that the students compute by hand, by pen and paper. So you can see what is happening right now. For students, math equals computation. This is a target, right? This is a target for them. They will target this. But for educators too, and this is what I think is somewhat of a problem. For educators also, math is computation, and now it's both a pedagogical target and a metric of student learning. And this means that we are screwed. Because of why? Because of Goodhart's law, right? Goodhart's law is kind of a Dutch, and this is the Wikipedia page, and it says when a measure becomes a target, it ceases to be a good measure, right? And the way I like to think about it is something like uncertainty principle, but for policy, right? So imagine that you have some probability, some population, and there is goodness and badness distributed, probabilistically in that population. And that population is sentient and conscious, right? So you are gonna measure how good and how bad they are, right? And distinguish between individuals of that population. Well, the population is gonna become aware of your of your measures and then target those metrics specifically, right? And the good people will target those metrics, and the bad people will target those metrics, and you won't be able to tell which one is which. This is the better formulation. Any observed statistical irregularity will tend to collapse once pressure is placed upon it for control purposes. So let me reformulate the Goodhart's law for you, right? It's the reason why LLMs are not getting better despite their metrics being better. It's the reason why such a high fraction of high H-index scholars are so extremely incompetent, to the point that you talk with them and with your small H-index and you think, how, right? how does they how do they know? They don't know this thing, right? There is a lot of H-index maximizers among us. Not so many among you mathematicians, but in physics we have plenty of H-index maximizers. It's a disaster. Do you know why price increases have continued to increase while inflation has been steady, right? Goodhart's law. Olympic cyclists, we measure their hematocrit, right? So we ensure that they don't put EPO in their veins, and now they use little engines in their bodies. And then yes, my students fail to identify a function from this graph, provided that I put the graph outside the window that they expect it to be, right? So bottom line, recommendations: do your thing. That's my main recommendation. If, however you teach, you are a teacher of math. If for you math should be computing and factoring polynomials and solving all this little busy work by hand, that is fine with me. I love you the same, right? But this is gonna be more and more important, and we are starting to realize it's important in pedagogy. Thank you so much. I think I ran out of time already, but I kept it to 22 minutes. Email me if you have any questions or suggestions. I put a bunch of links in the description, including samples of assignments that you can reutilize in your teaching. If you build some learning experience from them, feel free to cite them or to acknowledge them. So thank you so much. I'm very sorry I couldn't be here with you today on Saturday. Goodbye.